Hello, everyone, and thanks for joining us today. My name is Kelly Quinn Sands, and I'm from NASA Glenn Research Center, and I'll be your moderator for this webinar today on shape memory alloy tubular structure. As part of my role at NASA Technology Transfer, I work with NASA scientists who've developed new technologies that may have applications outside of the aerospace industry. We patent those inventions and we market them to industry through our website, which I will show you later. Our presenters today are Colin Creager and Dr. Santo Padula II. Colin Creager is a researcher here at NASA Glenn Research Center and a recognized subject matter expert in paramechanics and surface mobility. He received his Bachelor of Science in Mechanical Engineering at The Ohio State University in 2006 and began working at NASA in 2007. His research primarily focuses on investigating concepts for enhancing planetary rover exploration, including novel tire technology development, alternative locomotion, and excavation techniques. He is the co-developer of multiple compliant tire technologies for planetary rovers, some of which have been infused into flight programs. He recently served as the tire design lead for the Mars Sample Fetch rover, and currently runs the Simulated Lunar Operations Lab, also known as SLOPE, at NASA's Glenn Research Center, which is a state-of-the-art facility for evaluating tires and mobility systems on simulated lunar and Martian terrain. Dr. Santo Padula II received his PhD in Materials Science and Engineering from Technological University and has worked full-time at NASA Glenn Research Center for over 24 years. Over the past 21 years, Dr. Padula has focused his career on becoming an expert in the field of shape memory alloys, also known as SMAs. SMAs are a unique class of materials that can store large amounts of energy by undergoing a solid state phase transformation that can be either thermally or mechanically induced in the material. Dr. Padula is one of the principal investigators of SMAs at the NASA Glenn Research Center, where the group is world-renowned because of their extensive expertise in alloy development, thermomechanical processing, and in situ neutron experimentation, mechanical characterization, and constitutive model development. As a result of his extensive expertise in the field of SMAs, Dr. Padula has served as the General Vice Chairman and Characterization Subcommittee Chairman of the Consortium for the Advancement of Shape Memory Alloys Research and Technology, also known as CASMART. His expertise in the field of SMAs has led him to be asked to develop testing techniques that can be used to direct standards development for the community and has created strong ties to the industrial suppliers of this unique class of materials. Dr. Padula's work has garnered numerous awards and recognition, as well as a number of disclosures and patents on SMA technology. In addition to his patents on SMA applications, thermomechanical processing, and alloy development, he's been the recipient of 2 R&D 100 awards. Dr. Padula has authored over 65 publications in the field of SMAs, which have been cited in over 2,000 other articles in the field, and he's recognized as one of the leading experts in the utilization of SMAs in complex structural forms. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box and we'll answer them during the Q&A session at the end. And at this time, I'm going to turn it over to Colin and Dr. Padula.
Thank you, Kelly. All right, like Kelly said, my name is Colin Creager. I work with Santo Padula here at the NASA Glenn Research Center. And our presentation today is going to be over a particular technology that we developed originally for bicycle tires, actually. It's kind of a spin-off of some lunar rover technology we've been working on, but we wanted to also talk about some other applications. So we're going to spend a little bit of time talking about some of the background. Santo's going to introduce you to shape memory alloys, provide an overview of this particular technology, and then spend some time talking about other applications, and then hand it back over to Tech Transfer for some licensing information and some questions and answers.
So to begin this discussion today, we're going to first back up and look at what most of you are probably very familiar with, which is conventional metal deformation. And we're going to do that so that you can understand the differences in the mechanisms that are utilized. Yeah, differences in the mechanisms between a conventional metal and its reversible capability, and then how an SMA actually works. Um, and so when we talk about conventional metals, predominantly elastic plastic metals, which are used for structural applications, if we look at the crystal level, what we see is that we have a crystal lattice that as we apply loads to that lattice and or structure at the global level, we will begin to stretch the bonds between the atoms that are comprised of that metal. And we can do that up to a certain limit in conventional materials. And beyond that limit, which we call the proportional limit, we will then plasticize the material, so generate irreversible deformation within the material, typically and usually related to dislocation motion, or what we conventionally call the inelastic mode of plasticity. If we want reversible deformations in a conventional metal, we have to design so that we stay within the elastic regime in that material. And in that reversible sense, we can only deal with the bond stretch between the atoms as a reversible mode within the structure. Next slide. In shape memory alloys, we have a very different mechanism that is activated. In these material classes, we actually, in the solid state, are doing a reversible phase transformation. It's known as transient twinning in these systems. And what we, in essence, are doing is we can start in one phase of the material. In this case, we're exhibiting an starting as an austenite. And then as we apply loads and stresses to the system, we actually induce a metastable phase transformation where we change the crystal structure from an ordered cubic to a monoclinic crystal. And so we actually rearrange the atoms in the solid state to a different crystal structure. That motion, since it's not just related to bond stretch, is capable of doing over 30 times the deformation that we could do in an elastic bond stretch in a conventional metal. And this opens up a new window of opportunity for us to utilize these much larger reversible strains within the structure to completely change the way we design a structure. In these videos, what we're going to see is a couple of examples of what we call the thermally induced transformations. So in shape memory alloys, we can utilize this phase transformation that exists in two different modes. We can thermally induce the transformation to create shape recovery, or we can utilize it in another mechanism, which we'll show later, called the mechanically induced transformation, where we can apply loads and stresses reversibly we can create large deformations reversibly just by loading and unloading the components. So in this case, we're going to show the thermally induced transformation. And in the left-hand image here, you're going to see two structures that were already deformed to where they look like they've been plasticized. But as soon as we add heat to the system, we can actually revert those structures through large deformation fields to their original component shapes. In the other case, on the right, what we're going to be exhibiting is the utilization of this thermally induced shape recovery, where we take any type of heat source. In this case, we have a cup of hot water. And in any gradient field, we can actually create a mechanism where we can use the gradient field to create shape change and therefore produce continuous motion. So this mechanism opens up a whole host of other capabilities for the material. In this particular case, we're looking at the mechanically induced transformation. And in these three videos, what you're going to see is you're going to see a comparison between the bending deformation of a tube made from brass, stainless steel, and a shape memory alloy, and the reversible potentials in each. So on the left, as we try to take a tube of brass and put bending loads on that tube, we get very little elastic deformation before we immediately go into plastic buckling of the tube wall. In case of stainless steel, we can take a similar tube, and if we apply those deformations, we get a little bit of elastic distortion before we begin to severely plasticize the system. And of course, in those two systems, none of that is recoverable. We've gone far beyond the reversible potential of those systems. However, in a shape memory alloy, because of this reversible solid state phase transformation that's available, we can put the same deformations in the tube and revert the entire structure back to shape. Again, we have over 30 times the reversible potential that we have in the elastic bond structure of conventional metals. Next slide. If we look at this from a classic standpoint of the stress strain behavior, what you'll see is that in the conventional metals depicted on the left there, we only, depending on how the material is processed and what material it is, we typically exhibit anywhere between 0.3 and 0.8% reversible strain that's available in the structure for design. Conversely, with SMA materials, we have a potential on the order of about 6 to 8% reversible strain in this solid state phase transformation. Next slide. In terms of our work at NASA Glenn over the last 25 years, our efforts in shape memory have really been focused in everything from applied research to alloy development and processing to testing and modeling, and of course the applications, some of which you've probably seen in the commercial or out in the public sector. But we look at everything from the atomistic physics all the way up to the component level. And within our group, we have one of the largest suites of alloys that exist anywhere in the world. Alloys and processings that allow us to do applications ranging from minus 200 C currently all the way up to almost 500 C. And we are currently working on some new classes of materials that will enable us to extend that range all the way up to close to 1000 C.
So I wanted to get a little bit of a history of how we got to this point where we're utilizing this shape memory alloy benefits and technology into tires. Our group here at NASA Glenn started doing mobility work and tire development back in the mid-2000s under what was the Constellation program for NASA, which is kind of an earlier iteration of the Artemis campaign to basically build an extended presence on the moon. So we built what we call the slope lab. We can simulate driving conditions on the moon, started doing some tire development work that kicked off by replicating, building, and testing the tires that were actually used on the moon during the Apollo lunar roving vehicles in the early 1970s. They recognized back then that they could not use pneumatic rubber tires on the moon and came up with a really novel invention, which consisted of piano wire woven into a flexible mesh. That then led to the development of what we call the spring tire. This was came out of a partnership between NASA Glenn and Goodyear Tire and Rubber out in Akron, Ohio. We utilized a lot of the same features, but used a different structural form, hence used a spring instead of a straight wire. So here's one of our early demos. This was a large vehicle at the time called Chariot down at NASA Johnson Space Center. This is several hundred pounds of force that the tire seen. Again, this is piano wire, which is a type of steel. That program went away, and then we started focusing on addressing durability concerns for Mars rovers moving forward. And this stemmed from damage that was seen on the Curiosity rover wheels in the mid-2000s. Here's a picture actually from the surface of Mars. Here's one of our spring tires on a durability test rig out at JPL. And what we found was that for the conditions that we needed to to accommodate on Mars, which are much more rugged than what we were designing for on the moon, we needed something beyond what we were currently working with. And this led to really the integration of these compliant tire technologies with shape memory alloys. So this was our first prototype and our first demo. These are nickel titanium shape memory alloy springs. Kind of similar to the LRV tire, these are several hundred springs woven into this flexible carcass or mesh. And you're seeing lots of deformation all the way to the rim, but fully reversible. We still use that tire for show and tells, and there's really no damage to any of the springs. And this is really kind of a culmination of decades of work, both on the rover and tire side of things, as well as the shape memory alloy side of things that Santo had been leading, which ultimately led to our first Mars spring tire technology, which has been patented and then implemented into future Mars, well, at the time, future Mars rover missions. So kind of the evolution beyond that point then. We built the first SMA spring tire in 2016. We actually then started exploring ways to adapt this for different load cases. We wanted to see if we could take this technology and scale it up for heavier loads, rather than a couple hundred pounds, a couple thousand pounds for both the long-term, say, mobile habitat type applications in space, but also for terrestrial applications. So this was a different version of an SMA tire that we call the radially stiffened tire. Ended up being a different patent, but also used the shape memory alloys in the structural form. And so we did a demo actually on Santo's boss's Jeep Wrangler. Other than a few scratches and a couple wires popping out, I don't think we saw any damage, and it seemed like it rode pretty well. Then we started scaling them down for the lower end, for lighter loads, smaller tire sizes, and this is really where we came up with the technology we're talking about today, the SMA tubular structure. So we'll get into more of that in a couple minutes. We started developing these for a fetch rover, which was going to be part of the Mars sample return campaign. We learned a lot about the tires since then. We also started looking into adapting this technology for aircraft tires. There was some interest from aircraft and landing gear companies. And so we've been putting some thoughts and effort into that. And then around 2022, the SMA tire, actually a couple of these technologies were licensed for commercial applications, mainly bicycle tires. And then we've also seen some interest in this technology for commercial lunar rovers, which is really kind of where space exploration is going. It's going to be lots of industry-led rover and lander designs. And so going back to this SMA tubular structure technology, or what at the time was the bike tire, our motivation at the time was really to see if we could take the structural SMA tire idea and scale it down for smaller applications. And it just kind of so happened that we were working with, who was an intern at the time, Calvin Young, who you might have saw his name on the first slide, had been working with us for a couple years, and became a really, really bright guy, became very knowledgeable in this technology, and also rode his bike everywhere. And we thought this would be a great chance to try it out on a smaller scale. And so his project with us for summer was to take what we thought would be the spring tire and scale it down for a bike tire application, basically a retrofit, take an off-the-shelf rim and add SMA springs to it. And he came up with a really clever way to do that, which involved a couple of different layers, which I'll explain on the next slide. But this then demonstrated that we could take something that was developed for a certain, say, rover class size of applications, and so that it could still be used for something like a bike tire or a scooter tire. So this particular structure, again, this was primarily using materials that we had on hand. So this is kind of just the first way to do this, and I should say up front, we don't envision that long term, if somebody wants to use this technology for whatever application, it doesn't have to be made out of springs. This is just what we've been working with and what we had on hand. You could use any sort of SMA structural mesh element, and that's something we've been planning to explore as well. This one in particular started out with 2 layers. The first one, I think of this as kind of like a slinky. It's basically the base layer of the primary nickel titanium structure. This large coiled wire really sets the cross-sectional shape of the tire as well as the overall stiffness. But of course, it has no lateral or torsional rigidity, nothing to hold it in place. And so these other springs, which actually were ones that we had been using for a Mars spring tire, we found that if we weave them circumferentially around this first layer, that only sets the spacing, but it gives it that rigidity that we need. And so this shows how we could wrap it around the whole thing. Eventually end up then with this final tube shape. Now you can imagine by adjusting, the geometry of both sets of these springs, you can come up with all sorts of different stiffnesses, shapes, sizes, whatever it may be. This is just an example of sound, just a load test we did on this. So you see how compliant it is. Now, before we actually integrated it with the bicycle rim, there was kind of one final step. This is something that Calvin discovered, is that by just weaving them together, you do add quite a bit of stiffness, but you still have a little bit of, we'll call it torsional flexibility, meaning that, as you're driving the tire, it will kind of flop forward or backward a little bit. But if we twist these so that you really lock everything in place, that makes sure that both structures are fully engaged and also pre-stresses the wires on the material, and that adds a lot of rigidity. So you take the tube, twist it, hold it in place, and then mount it to the rim. And then for our sake, we put a kind of a rubber, it's a material called Plastidip. It's like a rubber brush-on material, but you can envision using just regular rubber tread on here as well. And so before Calvin left for the end of the summer, we did our first demonstration. I'll show at least a little bit of that right here. I don't need the music. So in this case, it's the front tire is the shape memory alloy tire. And again, this is just retrofitted on an off-the-shelf rim. This particular one was built for road bikes, but there's no reason that you couldn't scale it for mountain bikes or whatever your application is. And like I said before, this also doesn't need to be made of springs as well. One sort of option that we've looked into is think of like a woven mesh made of finer wire that could even reduce your mass further and give you a little more flexibility and design space to work with. So if you're interested, I think this whole video is available online. I won't show it all right now. So to just kind of summarize some of the benefits, the near-term benefits, meaning if you're just taking an off-the-shelf rim and swapping it out and putting, an SMA tire on it, obviously you have safety benefits. It's puncture resistance. There's no chance of a flat tire. You never have to pump up your tires or never run underinflated. So you have efficiency improvements. And then sustainability, you're not replacing rubber all the time. You don't need your rubber. Even if you have rubber on the tread for grip, you don't need to encase the whole tire in rubber. You don't need it to be thick to prevent against puncture. So you cut down a lot of material waste there. But really where we see these benefits in addition to those is kind of opening up the design space for in this case, the bicycle. We'll talk about redesigning the whole bicycle wheel around this. You no longer need a tube, rim, or tread to be separate. This could potentially be one piece that you buy as one unit, which could reduce weight overall. You could redesign the brakes to be more optimal. They could be nearer to the tread surface, but you can also come up with different shapes. You don't necessarily, your tire doesn't have to be a perfect circle. You could make with the SMA, you can make a cross section that's more ideal for your application, say a flatter contact if you're doing off-road cycling. Again, want to reiterate, springs are not the only option. It's just what we had to work with to start with. And I think there's lots of other applications, which is how I will now hand it back over to Santo to talk about.
Yeah, so this particular structure is, part of the lineup that we envisioned for tire technology, but this structure in particular is also highly envisioned for a number of other types of applications within commercial market space. So first one is a number of different sealing and gasketing applications. So we can use concepts, if you're familiar with them, like the energized spring seal for improved interface capability. So we can design these tubular structures, as Colin mentioned, both in terms of their overall mechanical performance as well as their shape, in order to facilitate improved sealing, both in terms of regular enhanced flange connection, but also for low permeability docking seal applications. Next slide. We also envision a number of industrial coupling applications, again, because the SMAs provide anywhere between 10 and 30 times the reversible strain, depending on what alloy they're made from and what the processing is. We can do very high flexible type of couplings, things like high strength, high flexibility, cable pullers and connectors, to eventually developing structures that will replace bellows-like systems that have inherent issues with fatigue and other things. We can now use these materials to develop braided forms of those that are also impermeable. And then obviously, as you see there on the right, extremely high flexibility industrial couplers to replace what the capability is over what is conventionally done in the industry today. Next slide. In terms of biomedical applications, there's a whole host of others systems that we can do. We envision these tubular structures as a third generation advancement for the capability of stents and other biomedical implants for the body. Nitinols, which is one class of shape memory alloy that is used every day in the biomedical world inside the body for everything from arterial stents to catheter deliveries to bone staples to fixation plates. So these tubular structures are highly envisioned to be that next generation of biomedical implant technologies. We also can utilize them in fabric form, as you see there in the middle, for internal structures, for advanced, highly flexible, active and passive structures, for both endoscopes for the body, as well as sophisticated and advanced bore scopes for industrial use applications, as well as downhole drilling and other types of mechanisms for the oil and gas industry. It gives us tailorable pointing device capability, both either mechanically induced or thermally induced. We also envision the utilization of these structures in wearable devices, again, for biomedical, but also for other technology areas where we can utilize the properties of SMAs in the thermally induced systems to have wearable technologies that will aid for things like helping with circulation and other types of things for the human body. Next slide. In terms of other clothing or wearable applications, there's a huge opportunity to incorporate SMA technology into other textile technology in order to have wearables for enhancing athletic performance or aiding in bracing, as well as incorporating into other types of clothing or athletic wear in order to do dissipation and damping and or energy absorption and recovery. So SMA wire filaments, where we're at right now with the technology is we can produce them down to about 6 microns in size, or very close to the size of the diameter of your hair. And we can utilize those wires or filaments to incorporate back into conventional polyester or other type of textile yarns. And then we can take those incorporated yarns and turn them into any type of fabric that you want. So it enables a lot of the creation of various hybrid products. Next slide. And then finally, one of the other areas that we envision is for refrigeration and pumping applications. And this might be a little bit not commonly understood right now, but with SMAs, because this is based on a solid state phase transformation, every phase transformation has the ability to leverage the enthalpy of the transformation. There's a heat exchange every time the transformation happens. And so we now have the opportunity to use solid state devices in order to utilize that enthalpy of transformation to create various things. The field is called elastocalorics, and we can utilize that enthalpy of transformation to do refrigeration and or heat pumping. So this is a vastly expanding community in the SMA world, and these tubular structures could enable us to do inline versions of that type of system to replace conventional vapor cycle compression, heating, and cooling without all the hazardous refrigerants and bulky hardware. The other thing that we can do with them is because we can thermally activate them. Now you can see there in the lower right, we have the potential ability to utilize these tubular structures and encase them, and then use those for various things like hydraulic or other type of fluid lines that allow us to do inline pumping and get rid of all of the bulky equipment associated with other technologies like is needed for peristaltic pumping. Next slide. Finally, we circle all the way back to our envisionment of utilizing the tubular structure for alternative wheel applications than what's previously been mentioned. And we have the opportunity to go back into the biomedical world and aid humanity by creating these, compliant architectures based on this technology to facilitate more comfortable ride and energy absorption for disabled people that are bound to wheelchairs, but also for EMS gurney and even intra-hospital gurney to remove the more rigid wheels that are needed for the low or no maintenance on those systems, with a more compliant system that helps to prevent extra issues with, jarring or pain for a patient that's already having a difficult time.
Yeah, and I think this is our last slide, just to kind of summarize. We really see a lot of potential and lots of different applications for this technology or some form of it. And on the left, we have a lot of the airless tire applications, both on Earth and in space. We think of rovers as being pretty big, but there's also lots of plans for commercial rovers that are much, much smaller. Think like tabletop ones that might be able to utilize this sorts of technology. Then, of course, all the different biomedical seals, couplers, all the other applications that Santo highlighted as well. So I think with that, then we'll turn it back over to Kelly.
Thank you, Colin, and thank you, Dr. Padula. We do have a number of questions in the chat. That was a great presentation, very interesting, lots of possibilities there. Before we get into the Q&A, I'm going to give a brief presentation about our technology transfer program at Glenn. So we've got the slides up there. Thank you, Hia. And if we can just go ahead to the first slide. We're going to talk about technology transfer. Technology transfer has been a part of NASA's mission since its formation. NASA is encouraged to share its work for the benefit of all. In fact, technology transfer is congressionally mandated. And NASA Glenn Research Center has prioritized technology transfer by developing partnership opportunities that promote innovation, NASA technology commercialization, and small business growth within Ohio and the nation, and enhancing communication and collaboration with industry, academia, government, and other federal research laboratories throughout the United States. Next slide, please. NASA has 10 field centers located throughout the United States. And in addition to our field centers, NASA has many installations where highly specialized testing, building of aircraft and spacecraft, and verification occur. NASA Glenn Research Center's Lewis Field is located in Cleveland, Ohio, along with the Neil A. Armstrong Test Facility, which is located nearby in Sandusky, Ohio. Each field center and installation provide unique services, research, and technology to further NASA's missions. Next slide, please. Core competencies. NASA Glenn develops novel technologies in a number of key areas and is the center of excellence for power and propulsion, along with materials and coatings for extreme environments. And you can see in the bullets there some of our areas of expertise. The next slide. And our patent portfolio. Glenn Research Center patents roughly 10% of all invention disclosures submitted, and Glenn has over 200 patents and patents pending that are available for license. And those are viewable at our website at technology.nasa.gov/patents. Next slide. The Technology Transfer Office has worked very hard to make finding NASA's technology easier by creating the industrially relevant categories that you see. All patented and patent pending technologies for each field center is sorted into the categories, which can be browsed or searched on our website. And then we have some other partnering mechanisms. We have licenses, software usage agreements, and Space Act agreements. Next slide, please. Licensing from NASA is easy. We offer 3 types of license agreements to meet your needs. First, the evaluation license agreement that allows for a test drive of NASA technology. It has a set fee and a set term of 1 year that can be renewed annually for up to 3 years. The evaluation license allows a licensee to investigate the commercial viability of a NASA technology with minimal risk. The evaluation license is not a full rights license. NASA restricts the right to sell or offer for sale. And then there's the government use license, which is for entities seeking to use a NASA technology in support of a U.S. government-funded project. These licenses have no fees or royalties, but they do have a term matched to the period of performance for the U.S. government-funded project. And this is ideally suited for SBIR, STTR, contracts, grants, and co-op agreements, and in some cases, Space Act agreements. This is not a full rights license. The licensee may only use the technology in support of its U.S. government-funded projects. And then finally, the commercial license. This is a full rights license that is individually negotiated, and these licenses can be non-exclusive or exclusive in a field of use. Next slide, please. Software usage agreements. In addition to patents, NASA also develops a large array of software codes to support our mission work. And NASA makes these software codes available to U.S. entities at no cost. And as you can see here, the software is organized into convenient and industrially relevant categories to make searching and browsing easier. And we transfer these executable software codes via a software usage agreement. Software usage agreements contain terms and conditions specific to the release of that particular code. And to search or browse available software, you can visit our website, software.nasa.gov. Next slide, please. Space Act agreements. NASA also partners with industry and academia using the Space Act agreement. Space Act agreements are very similar to cooperative research and development agreements. They outline the statement of work, specific tasks and milestones, who's paying for what, data and intellectual property rights, liabilities, etc. Space Act agreements come in two flavors: reimbursable, where the partner pays for NASA's costs to perform the work, and non-reimbursable, where NASA pays and the partner pay their own costs for performing the work. Generally, non-reimbursable Space Act agreements are used when the proposed work furthers NASA's missions, and reimbursable Space Act agreements are used when the proposed work is in line with NASA's missions, but does not help advance them. There are a number of other factors that go into making this decision, and Glenn's Space Act agreement managers are available to assist in making this decision. And the next slide. Thank you. NASA's Technology Transfer Office is available to assist you. And please feel free to reach out to myself or my colleagues, and we can assist you with whatever it is that you're looking for. Now we'll move on to the question and answer portion of the webinar. So we've got a lot of questions. Thank you to everyone who has submitted a question so far. Please feel free to keep putting your questions into the chat box. And if you have any questions for me about licensing, I can answer those as well. And if for some reason we don't get to your question by the end of our time here today, we will follow up with you by email after the webinar today. So let me go ahead and look in the chat box. It looks like we have a few here already. So I'll just start at the top from Dennis. I'll just throw out the question, and Colin or Dr. Padula, you can figure out who wants to answer this. Where do you see some of the highest value proposition or high impact, high payoff in commercial market products, industrial products, biomedical devices, etc.?
Do you want to field that one, Colin?
Not necessarily. No, I think you have a better sense than I do.
Yeah, so I think it's like, it's really across the board. We have three main legs that shape memory is being looked at for out in the industrial markets. And the predominant one that exists right now, where there's tons of products already being leveraged and used, is biomedical. But the actuator community, both in terms of aerospace as well as in terms of automotive, is very quickly expanding. And then the third leg is what we call structural pseudoelastics, which the tire is kind of a form of a structural pseudoelastic. So same principle as the way that we do it in structures in the biomedical world, but at much higher loads and in much more extreme environments. So all three of those are really beginning to take off, and the sky's really the limit. This is the first revolutionary structural metallic material that has existed that promises to open up a whole range of new abilities with structures because of the reversible potential.
Great, thank you. Okay, next question. How often can the process be repeated without defects accumulating at the grain boundaries?
Well, that's a tricky question because it depends on how you design the system. You know, for a lot of the applications, if designed correctly or smartly, as long as the material, you know, basically it hasn't fatigued. And I'm sure that there's a question somewhere in there about fatigue of these materials. And what I'll tell you is that already in the biomedical applications, we're well within the millions of cycles. In automotive, for actuation applications where it's a thermally induced system instead of a mechanically induced system, we're also well within the millions and millions of cycles. We are currently pushing to new alloys and processings that promise to extend that up into the 10 to the power 7, 10 to the power 8 range. So these materials now, like everything though, if we drive these materials within the structure trying to get every little inch of reversible strain in the system out of it, we can impact that and see lower lives, so higher debit on margin. But if designed properly, these can adequately perform the same numbers of cycles as conventional systems.
Thank you. Okay, and then we have someone who wants to know if we have tech for Venus applications.
Not quite yet, but we're eking up on it. 500C environment and sulfuric acid is a tough boat. SMAs don't have very many problems in the environmental part of that condition, but the work output potential for the 500C is limited, although there. But that's why we are currently working on new classes of alloys that look hopeful and promising to extend that temperature capability all the way up in the 800 to 1000 C range.
Great. Okay, next question. What temperature ranges does the crystal hold deformation elasticity? Does it break in the cold and melt at higher heat?
No, these are, well, so I'm not sure if I understand the question exactly, but I'll try to answer it. Hopefully it answers the question. Can you repeat the question one more time, just so
We have, what temperature ranges does the crystal hold deformation elasticity? Does it break in the cold and melt at higher heat?
Okay, so like I kind of tried to mention at the beginning, this is not related to elasticity. So the term in the field, superelasticity or pseudoelasticity, is actually a very miscoined term. It came from the era and the days when they didn't understand what this mechanism was. So all they saw was this much larger reversibility, and so they just called it super elastic, but it really has nothing to do with bond stretch. This is a solid state crystal transformation that we do, where we're rearranging the atomic structure between two crystal lattices. So from that standpoint, we can do this pseudoelastic type effect. Again, miscoined term, but this highly reversible, mechanically induced transformation is how you should think of it. We can do that effect currently with the alloys and processings that we have today in production. We can do it everywhere from about minus 130 or 150 C all the way up to close to about 400 C repeatably. I'm currently working on new classes of alloys that will let us extend that down to about 40 Kelvin, which is a little bit beyond minus 300 C. And again, we're working on other alloy systems that will let us go the other way to extend this capability all the way up to close to 800, 900 C. For the mechanically induced transformation. The thermally induced transformation is slightly different. And so the answer there is slightly different, but we're working on ranges of alloys that are going to allow us to go over pretty much anything you could think of.
Great, thank you. We have another question here about the tires. None of the tires require any thermal heating to recover, is that right?
That is correct. Those leverage the mechanically induced transformation. So as fast as you can roll them through footprint, so load them and unload them, they will basically accommodate the energy and you'll be able to use it for that effect.
Okay, great. And then moving on, next question is, what factor decides the repeatability of SMA wire actuation? Working temperature or transition temperature?
It's a little of both and more of another factor. So as with all phase transformations, there's in the real world, there's hysteresis associated with it. So we have a set of transformation temperatures that are associated with each alloy and processing. And in essence, we have 4 transformation temperatures. We have what we call, and this is for the thermally induced transformation. We have an austenite start, an austenite finish, and that has its own small temperature shift that's associated with it. Then we have on the reverse process, we have a martensite start and a martensite finish, and that has its own temperature difference, usually on the order of a couple of degrees C for either one of those legs separately. And then those two legs are separated by we call it the major loop, or the major hysteresis between forward and reverse transformation. And those typically in real world materials that are available in production are anywhere between 20 and 40 degrees C. So you have to operate over that. If you want to operate through the full transformation, you have to operate over a 20 to 40 C, depending on alloy and processing range of temperature. We're constantly working on bringing that hysteresis down to as small as possible, with the intention of getting it anywhere between 5 and 10 degrees C. That's for the fully reversed actuator potential that would be a replacement for a hydraulic or pneumatic actuator. In other applications where we only need to activate one time through a transformation, let's say, to do a shape recovery for some one-time use application, we only deal with one of the two legs, and therefore that thermal change that is required to activate the system is only on the order of a couple of degrees C.
Okay, thank you. We've got quite a few more questions and just a few more minutes. We have someone is asking about cost. I don't know if that's possible to estimate a cost per yard / meter for these applications. Is
Yeah,
that even...
so when we talk about these materials, if we like typically in the industry, like if we're looking at wire, we would talk about it in terms of a lineal foot cost. And so where a product like conventional steel or a stainless or something of that nature in wire form for a given size would be on the order of, 2 to 10 cents, depending on the alloy or processing per lineal foot. SMAs at retail cost are somewhere on the order of anywhere between like 80 cents and $1.25 a lineal foot. Again, depending on alloy and processing. So, and of course that's, for those costs are typical costs because some of those application spaces aren't in ultra high volume like steel is, already. But as these volumes of scale continue to grow, those costs will come down. But as of right now, they're roughly in the 80 to $1 a lineal foot range compared to what the lineal foot cost for conventional is.
Okay. Okay, let's see. We've got someone is asking, can this technology be used for vibration dampening as well?
Absolutely. So as with any hysteretic system, we can use the hysteretic nature of the crystal transformation to dissipate energy and to do damping. So we can do actual, when you think about damping applications, we can actually tackle the process two different ways. So one, we can use it directly like is commonly thought about, where we actually dissipate the energy as would be done in like a common dashpot type system or Maxwellian coupled construct. The other advantage of SMA technology is that we can actually use the phase transformation, where we basically think about it in the sense of, if we just change the temperature of the material, because we will cause a crystal transformation, associated with that crystal transformation is property change. And so we can actually shift the inherent stiffness of the structure just by changing its temperature. And if you think of it that way, that gives us another mechanism where it allows us to actually shift a natural frequency or resonance mode within the structure to a completely different state as we approach it, thereby not even having the vibrational energy available, come into the system. So we now have opened up two an alternate mechanism of being able to deal with dissipation and damping, depending on what the energy is coming from, vibrational energy is coming from.
Great. Let's see. I think we have time for one more question, and I'm going to ask this one. Someone is asking, can you say more about clothing applications?
That's a pretty wide topic. Yeah, we have a lot of we have the capability to use both the thermal and the mechanical part of the system to create textile architectures that can be used in wearable applications. And one of the ways that we're using that in the space program is to aid astronauts for various parts of their spacewalk or other mission architectures. A lot of times with the gloves that the astronauts wear, they're extremely stiff and rigid because of the way that they are designed, at least currently. And that makes it very difficult for them to do gripping applications, and it also leads to fatigue and other things for the astronauts because they're working against a fairly high, bending load within the glove. And so we can actually incorporate passive and or active elements of SMA within new architectures where we can create or reduce some of that force that they have to apply manually by actually activating the glove and leaving it on so that the glove will actually want to curl to some degree, and then they have to use less of their own manual force to keep that glove attached to something, holding on to something. So that aids in fatigue and exhaustion of the human being. In other aspects, we can do that passively where we design it into the glove and give them other capability. So it really depends on the application. When it comes to sports and leisure and all these other things, same things are possible. We can have now design a structure that uses active or passive elements to offload the body or reduce the stresses on the body, or absorb energy or dissipate energy and the like. So it really opens up a whole new possibility for how a garment is designed and developed to do its function.
Fascinating. Thank you. Well, I would just want to ask one final question, and thank you everyone for all these great questions. The remaining questions that we didn't get to today, we will respond via email. But Dr. Padula, I have one final question, and that is for medical devices that use the shape memory property, how tight is the transition temperature? Can the transition occur with a 3 or 4 degree temperature change?
Yeah, so mainly in the biomedical world, the predominant mode that is utilized is the mechanically induced transformation. So those alloys are designed so that they're the transformation of the crystal is just slightly below room temperature. And so we sit as this parent austenite phase, and then as the structure is loaded in the body, it metastably transforms to the martensite to accommodate the deformations. Because it's that mechanically induced transformation, there really is no temperature change that's necessary to induce the shape memory properties. It's a mechanically induced event. So they're designed so that their transformation is just below room temperature, such that at 37°C, which is the temperature inside the human body, they exhibit the properties naturally through the mechanically induced behavior. We don't currently, there's only a few one-way type of thermal transitions that we do. So as an example, it would be a bone staple. So in a bone staple, the way that that's used is that device is designed for the shape that we want it to be once it heats back up to the human body temperature. And then that particular staple would be thrown into a dewar of liquid nitrogen. We call it cryocooling. It would be cooled down to its lower temperature state where we could easily deform it into a new structure and then have it kind of maintain that structure until it heats back up to the body temperature. So that would then be taken out by the doctor right during surgery, implanted in the deformed shape. In the case of a bone staple, think of it as spanning two broken bones. It would be deformed so that it would be punctured into the two broken bones. And then after we closed the patient up, as that was heated back up, that bone staple would then return to shape where it pulled those two prongs closer together and load the bone. But now it's in its reverted state. It's a one-time thermal activation, and it then maintains that structure for the rest of its usage. So the thermal effect is only used in modes like that, one-time effect inside the human body. And part of the reason for that is because to drive an actuator inside the body currently, the amount of thermal energy that would be needed to elucidate the properties within the shape memory would be damaging to the surrounding tissue. So we only use these in the biomedical world currently in these very limited one-way type transitions thermally, but then predominantly only in the mechanically induced system where no temperature change is required to elucidate properties.
Great answer. Thank you so much. Thank you, Dr. Padula, and thank you, Colin. What a great, interesting webinar. And thank you to everyone who asked such great questions. I know there's quite a few more in the chat, and we will respond to you via email afterward. Very much appreciate your time today. And thank you for being with us. Great presentation, and have a great rest of your day.
Thank you.
Take care.